All right, my name is Chris Wickman. I am going to give you the basic overview of research design, and we'll talk about developing a research question in this particular lecture. First thing I want to kind of talk about is the 10,000 foot view of research studies. So if we kind of stand back and think about what are we actually doing, there's two general types, at least from a statistician's perspective, of studies out there. There are experiments, which are there to explore cause and effect. And these are always prospective in nature. We set it up, we bring in our subjects, our experimental units, we apply our treatments, and we wait and watch, and then we get our answer at the end. So these can be something along the line of a clinical trial. We can do teaching method comparisons. We can do guideline changes. We can do different methods for treating an injury, that type of thing. And what distinguishes an experiment most of the time is that the subjects or the experimental units are randomized to the treatments. So we actually randomly allocate what each subject is going to get. An observational study, on the other hand, is looking at exploring associations. If you're trying to go out, do an opinion survey, that type of thing. And you can also use it to potentially establish some parameter estimates to help you, figure out where should I be starting? What am I trying to change? What needle do I need to move, so to speak? So an observational study itself can be retrospective, it can be prospective, or it can be a snapshot in time. The difference here is that you take what you get, right? There's no randomization. You can't apply anything to subject because you're literally just observing, thus the name observational study. And there's a caution here. It may be biased. It doesn't necessarily mean that it is, but it could be a biased study. And regardless of what type of study we're out there, you can always use the scientific method to kind of guide your way. So I use a 6-step scientific method. I know other people use, a 4-step. Some have as many as 8 steps. It doesn't really matter. The premise is kind of the same. So if we think about statistics, statistics itself is defined as basically making decisions in the face of uncertainty. And along with that comes aspects of statistics which come to study design. So that's how am I going to collect my data? How am I actually going to get at the outcomes I'm interested in? Then we have a section in statistics where we're trying to describe the data. So we're going to organize the data, we're going to summarize the data, we're going to analyze the data in some way, shape, or form. So whether that's a plot or a table, a summary table, finding a summary statistic like adding everything up and dividing by the total and coming up with the mean, that type of thing. And the last piece we do in statistics is the inference. And here's where we're trying to use all of our analysis, everything we've done, and we're going to make a decision. We're going to draw a conclusion. We're going to make a decision. We'll decide, did this work? Did it not work? And from there, reformulate an idea and move forward again. So if we look at this, the scientific method in the 6 methods that are 6 steps that I have here starts off with forming a hypothesis, then setting up the study, collecting the data, analyzing said data, draw your conclusions, synthesize your conclusions, your current result, with results from other studies. From there, form a new hypothesis, and the whole thing starts over again. And we can see with the various shades of arrows here that statistics can play a role, as a discipline, can play a role in each step along the scientific method. So forming a hypothesis, that one I put in as a dotted arrow because that's really the purview of the primary investigator to determine what hypothesis they want to test. Now, a statistician can potentially help once they know what kind of things are you trying to measure. How can I actually set this up to get at or set up a hypothesis that I can actually answer with what I can collect. But then setting up the study and how to set up the data collection tool, statistician can help with that. We won't specifically collect the data as statisticians, but we can help you organize it to where it's going to be easily analyzable after the fact. And then obviously our main focus, other than design of a study, is analyzing and helping to draw the conclusions. But again, the conclusion, and I'll say this over and over again in any class I teach, just because something's statistically significant does not mean it's biologically or clinically relevant. And that's really the researcher, the primary researcher's view on drawing the conclusion is, statistically may mean something or appear to mean something, but biologically it means nothing. That's important to know. Then helping to synthesize with current results. So that could be either your systematic review or a meta-analysis kind of concept. So a statistician may help you there. And then also in this, from the inference piece, we can help with the generation of new hypotheses. So Albert Einstein is somebody that I really admire as far as some of the views he had on science in general. And one of his quotes is that the formulation of a problem is often more essential than its solution, which may be merely a matter of mathematical or experimental skill. So, in other words, what he's basically saying is the most important, and this is often seriously the hardest step in any research project, is basically to identify and verbalize the hypotheses or hypothesis that is going to be tested, or the question that you're actually trying to answer. So, when we're looking at research design, what are some of the things we need to have in mind? Well, first thing is we need to have a context. Why is this topic important? Number one. Now that I have a topic that I think is important, or if I identify one that's important, what kind of study do I want to do, and what aims do I have for that study? Do I want to carry the football all 100 yards down the field and get the touchdown and prove the greatest thing since sliced bread, or do I want to attack this thing piece by piece and show in a more linear fashion and sequential fashion that I can actually, have some effect on outcomes? From those study aims, I'm going to generate hypotheses that need to be tested. Well, how am I going to test those? What methods am I going to use? That type of thing. But that's the context piece. Once I have the context kind of established, I get into what's known as treatment design. And if you think about, you might have heard explanatory factors. Well, that's kind of what we're after. I've got a treatment design, meaning I want to apply certain treatments to subjects and I want to see how those subjects react. Well, I need to know what treatments am I looking at? How many of them are there? How do I want to allocate them? And that all goes into treatment design. Another piece of treatment design is going to be what are things that can potentially confound what's going on. So if I'm looking at cancer patients, maybe the staging or the severity of the disease is going to confound my result. So I need to, possibly take that into account somehow. How am I going to do that? Maybe age, what I'm studying affects multitudes of ages, but age itself also has a multitude of effects, so I need to account for that somehow. How am I going to do that? Then the next piece is what's known as the experimental or the study design itself, and this is how that treatment design that we talked about before is allocated to my subjects. So the subjects that I'm actually studying, how are those treatments going to be applied to them or allocated to them? And that could be through randomization. It could be through, a convenient sample. We're just doing an observational study. But I need to understand what am I after there. Then once I've established what I want to do as far as my design, I get into this piece called a power analysis, or it's probably better to say a sample size analysis. And this is where we try to determine how many subjects do I need, whether it be animal, tissue, or human. But how many do I need to where I can actually get a meaningful result? So if there's a difference in there, I'll actually see it. And how many can I get away, or how few can I get away with without being too burdensome financially? So there's a lot of pieces going on in the sample size analysis. And then we get into the sampling design, which is how am I going to select my subjects that are going to be in my study. And then we'll get into data collection tool. So how do I actually, once I start collecting data, what do I put it in? How do I store it? How do I save it? And once all those pieces are in place, then you can move on and conduct the study. Now notice I have not talked about the IRB or anything like that. That's all buried in here. Or if you're doing animal studies or benchtop studies involving animals, you have to go through IACUC. Those are different processes that somebody else along your journey will talk to you about. So let's start off with context. So this is something I've run into a lot of times with investigators of all experience levels. But data collection with no plan usually leads to a lackluster result. So you're saying, how can that even happen? How do you start collecting data without any plan? Well, a lot of times people will just start saying, oh, well, maybe we should, start collecting these things when we have either patients or something come into the lab, or patients come into my clinic, that sort of thing. And they just start collecting it because they think it would be interesting to look at. But they didn't really design what they're after. They didn't really explain to anybody how do they want this collected. And you end up with this mishmash of stuff. Let's say you get different data entry people and they enter things differently compared to other people, or one person in the lab is going to measure counts by physically counting and giving a number every single time, and other people say, oh, well, 10,000 is the magic number, so if it's under 10,000, I'm just going to report under 10,000, and only those over 10,000 am I going to actually count. I've also seen it where pathology studies come back where some people are literally counting and trying to get a good account as possible, and others are literally saying less than 10,000, greater than 10,000, and not giving us any other information, and they're kind of missing what the actual intent of the study was. So that's one part of context. Next piece is you really, really, really want to focus on your own interests. All of you are in a graduate program of some sort, so you're probably going to have to do a research study of some form, and I would just highly recommend to you that you focus on things that you actually care about or you have curiosity about, because speaking from personal experience, if you work on a subject that you're not all that invested in, it makes it very, very arduous. Okay, so for each topic that you identify above, then you determine, okay, what kind of questions do I have? Once I have my questions, you kind of just list them out. You look at the question and you say, okay, is there an outcome I can get at to answer each one of these questions? If so, what kind of outcome is it? Is it quantitative? Is it qualitative? I need to know, is it a number or is it just kind of a feeling, strongly agree, strongly disagree, that kind of thing. And once I do that, I have to figure out, or once I figure out what the measure is going to be, how is it going to be displayed, right? So how do I actually get at it? Do I have to send somebody out and ask a question? Is it a relatively objective clinical measure? Is it a subjective opinion? Something along that line. And if I come up with a question where the outcome itself isn't directly measurable, how can I get at that, which is an entirely different course, but there are methods to get at things that don't have a direct measure. And then the last thing you want to think about with context is what type of conclusion do I want to draw, right? So am I here to say I prove the greatest thing since sliced bread, or I have an indication that this is true, or is my goal just quality improvement to make my clinic or my lab more efficient, that type of thing. So probably the best example I can give you for context, which is not experimental in any way, shape, or form, is imagine that you're traveling in your car and you start off with a full tank of gas and the location at which you start is 1,000 feet above sea level. You get in your car and you drive for 8 hours. You may refuel, doesn't matter. You've gone for 8 hours. When you stop, you get out at a location that's literally 1 mile or 5,280 feet above sea level. The question becomes, or the question that I have for you, is what does the topography, what does the landscape around you look like? Right? And some people may say, well, I've lived in Omaha, Nebraska my whole life. I know it's roughly 1,000 feet above sea level, and if I drive for 8 hours, I'm basically near Colorado, so I'm probably in an area that's still relatively flat, right? Because if you know, I can go 4,300 feet. I can increase my altitude 4,300 feet, but it's spread out over 454 miles. So I basically go up the thickness of a sheet of paper, or a 1/16 of an inch, about every mile in to get there. So that doesn't really help me. Then I'm looking at, I once lived in Crete, and specifically in an area outside of Hania, Crete. And if anybody's ever is familiar with the island of Crete, there's a mountain right in the center of the island, and you can start off literally at sea level in Hania, and it's about, I believe it's about 10 miles. You can be inside the national forest there at the mountain and be well over a mile above sea level, and that would take you, probably an hour just because of the way the roads are winding. But from a perspective standpoint, I could have driven around in a circle in Hania for 7 hours and then driven out there and gotten to the top of the mountain. So the context really matters. I need to know, what am I after? What arena am I operating in before I kind of march down my road of just collecting data for whatever reason. Okay, so what types of conclusions, what kind of purposes do studies have? So first and foremost, what we need to do is you come up with your question. The first thing you do is you do your lit review. Everybody's pretty familiar with this, I'm sure. So if your experiment, you find out what you want to do has actually been done before, and that's like, oh man, that's no good, I wanted to do that, it's okay to go ahead and replicate a study. The idea behind replicating a study is you're going to show that it has validity other places. Just because one site does it doesn't mean it's going to work at another site. So if you can go through and you can replicate what another lab or another clinic has done, that's great. That shows validity towards the method that you're looking at. If you can't, though, that's significant as well, because that says this may not be generalizable to every clinical or laboratory setting. The other thing that you can look at when you're looking at replicating studies, you can potentially address confounding systemic issues across different locations, which would be good to know. What if you get a different result? What's different about your setting versus a setting that it was originally done in? Another thing you want to look at for your purpose is, what are you actually after? Are you trying to prove something? Do you want to make comparisons? If that's kind of your goal, that's known as the main study, like a big quote unquote study, or a designed study is typically what you're after with a kind of prove purpose. If your goal is quality improvement, either improve the quality of lab work, improve clinical practice, improve workflow within the clinic or the lab, come up with better procedures for your clinic or lab, that's fine and good. The only difference between quality improvement, its purpose is that its near-term goal is to make a small finite set of people, procedures, etc. work more efficiently. That's all that is for. Doesn't mean you can't publish it and tell the world that, hey, we had this problem in our group, this is what we did, this is how much better we got. That's perfectly acceptable. Next thing we can look at is to provide a basis for a larger study, and these are known as pilot or feasibility studies. You can also look at a pilot or feasibility study as a way to generate discussion in your profession or community. So maybe you're interested in, and for that matter, to generate discussion, it could also be a meta-analysis or a systematic review. Maybe you've noticed something about a bunch of different articles that have come out and realize, hey, something's changing in the care of, let's say, breast cancer or COPD or something like that, and you want to generate discussion in your profession at a professional meeting or whatever. That's another reasonable way to do that, is to put a pilot together, do a feasibility study, or go and do a straight up systematic review or meta-analysis and not actually quote unquote get your hands dirty with an experiment or a study. Okay, so the next thing you want to do is, once you've got all that kind of in your mind, you've got your context settled, you got your purpose, you want to write out your research aims, right? So we've got our topic, we have our questions that we're interested in, and we've already talked about, what outcome measures I'm going to identify, and we have our purpose. So to write a research aim is, you basically need to summarize all that we just talked about into 2 to 3 sentences. So the first sentence is usually kind of the research question. The second sentence is kind of an associated hypothesis. And a third sentence is put in if there's additional information that provides the context of why you're doing this. So the example I'm going to use is a study I worked on a few years ago, and it was looking at a trauma patient's exposure to ionizing radiation. So it was a 10-year retrospective study, so there's no experiment involved, no treatments applied or anything like that. So the research question started off with the cost and availability of imaging technology, specifically in this case CT scan, have decreased and increased respectively. So the availability has become greater and the cost has gone way down. So the question was, has this had an effect on trauma patients being exposed to ionizing radiation? So the hypothesis that they came up with was, for similar injury classifications, trauma patients exposure to ionizing radiation will have gone up over the past 10 years just due to the fact that this additional information is the access to whole body CT has made its use much more common today than in previous years. So they're basically trying to tie it together with they believe it's CT. Now, are we going to prove this? Not necessarily just by looking at the exposure, but we could look at, the counts of the types of pictures that we'll be taking. Are we talking about MRIs? Are we talking about X-rays? Are we talking about CTs? And we can see, are those numbers shifting over time? Okay, so the treatment design in this case, what we need to look at is which population of explanatory variables are to be examined. This is controlled by the researcher, right? So the factors that we're looking at is the injury severity score. We want to use that to explain ionizing radiation exposure. So the injury severity score basically ranges from 0 to 75 if you're not familiar with it. They split the body into 6 regions, I believe. They score each of the regions on a scale of 1 to 3, I believe. Maybe it's 1 to 6. Sorry, I don't remember off the top of my head. And then they square that score and add up the top 3 regions, and that gives you your injury severity score. So I've got 1 to 8 is a mild, 9 to 15 is considered moderate, 16 to 25 is severe, and then anything over 25 is a critical type of injury severity score. So that in and of itself is kind of ordinal, right? It's more the importance level, or the critical factor, gets higher and higher as the ISS moves up. Okay, so now we need to look at something like treatment designs. What can I do with a treatment design? So in this case, in my example, we have a single factor. All we're looking at is injury severity score. That's a pretty basic study. We could have done more trying to account for different things. But this would be called a single factor. So literally one factor with 2 or more levels. So injury severity score, we have 4 levels. Another example would be a pain medication, 500 milligrams, 250 milligrams, and placebo, but all the same pain med, just different dosages. We could do a multi-factor main effect, where we're looking at 2 or more factors having 2 or more levels. So I could look at pain medication and say speech therapy types, and then I can do what's known as a multi-factor with an interaction. And what an interaction says is that, let's say, in this case, we're using pain med and cancer stage. So I have 2 or more levels at each one of these factors. And an interaction is saying that it's possible that a pain medication is less effective as a cancer stage increases, saying that the effect of the pain medication is mitigated or tempered by the cancer stage. And that would imply that there's something going on. I can't just say there's some main effect of the pain med. So if I take this pain med, 90% of people are going to feel pain relief. That's not necessarily true. It may be that, that's true in cancer stages 1 and 2, but maybe 3 it's not as effective, and maybe in stage 4 it doesn't even work at all. That's what we're talking about with an interaction. Okay, so we have these titles, if you will, or names for different types of studies. And the first one I want to talk about is the pilot/feasibility study. And this first definition comes from the National Cancer Institute, and they call a pilot study an initial study examining a new method or treatment, period. They don't get too wordy with it. Then I get into the United Kingdom and I can't remember what AQR stands for, I apologize, but it's basically their National Health Service research group. They consider a pilot study a small study conducted in advance of the planned project, specifically to test aspects of the research design, such as stimulus material, and to allow necessary adjustment before final commitment to that design. So in other words, they're basically saying a pilot is a mini version of what you're trying to do on the large scale level, but you're just doing it to test, are all my procedures working? Is my protocol correct? What kind of things do I run into either in the clinic or the lab that cause problems? Do I need to adjust something in my protocol to account for that type of thing? Or maybe you find out that you're doing, say, ELISA in the lab, and that the plates that you've purchased or you intend to use aren't good for what you want to do, or maybe you find out ELISA isn't what you want to do and you want to end up doing mass spectroscopy or something like that. that's basically what the idea behind a pilot is in their eyes. They also, the same group out of the UK, defines feasibility as a separate type of study. The definition here for feasibility is a little bit different than the one that the UK gives. This is actually from a preventive medicine journal, and they define a feasibility study as being used to determine whether an intervention is appropriate for further testing. So in other words, they're saying, is the intervention efficacious? And then they enable the researchers themselves to identify whether or not the ideas and their findings can be shaped to be relevant and sustainable. So sustainable means once I take it out of a protocol-driven, highly controlled environment, does it still appear I'd have a bang for my buck? Is it going to matter? And further, they go on to say that feasibility studies may identify not only what, if anything, in the research method or protocol that needs modification, but also how those changes might occur, or how can we make it more efficient. So I guess the long and the short of it is, depending on what discipline you talk to, whether it be healthcare, behavioral science, etc., there's different definitions for pilot and feasibility study. A lot of times, if you look at NIH's website, they use the term pilot and feasibility interchangeably. When you get into, when you go over to England, they treat them as two separate entities. When you get into things like the behavioral sciences, they, depending on which type of behavioral science you're looking at, or psychology studies, they sometimes treat them as two different things, and sometimes they say they're the same thing. So the long and the short of it is, if you're planning a pilot or feasibility study, make sure everybody you're talking to that's going to be helping you with your study design understands, if you're using the word pilot, what do you mean by that? If you're using the word feasibility, what do you mean by that? If you're using the word efficacy, what do you mean by that? Make sure everybody is on the same page as far as definition. Okay, this is from the National Cancer Institute. They only gave a definition for pilot, but they used the word feasibility all through their writings about pilot, so they basically interchanged the two terms. But some of the questions they say can be answered by a pilot are, can I get to my target population? So who is my target population? How can I get to them? Once I get to my target population, is it reasonable for me to actually be able to randomize them to the treatment groups I'm interested in? Once I get these participants to join the study, can I keep them in the study? Or if this is an animal study in a lab, once I get them on my protocols, is there anything that I didn't foresee that's causing either the animals to die, or they are in so much pain that they're required, by IACUC to be taken off the study, that type of thing? I'm going to lose potential dropouts, basically what we're after. If you're talking about human studies, a lot of times what you'll do is, I've seen studies where we're going to ask them all this stuff. We're going to go through these 5 different surveys. We're going to do these types of tests all at every single clinic visit, baseline 6 months, 12 months, all the way out to 3 years every 6 months. Well, people will find out very quickly that survey fatigue is a very real thing, and people will drop out because they just don't want to keep doing the same thing over and over again. So you really have to be cognizant of what you're asking participants to do, and then once you decide on this is what I want them to do, getting a small cohort to find out, will they actually do it over the time frame you're interested in. Then the next piece is, I've identified these treatments, but can I actually deliver them per my protocol? Again, is my protocol good? Are assessments too burdensome? And it may or may not be, but people will tell you if they tire of doing something like the 6-minute walk and that kind of thing, if you're doing that over and over and over again. Are the treatment conditions themselves acceptable to participants? Is there something that you didn't realize, because a lot of people are on different drug regimens other than what you're studying. Does anything you're studying combined with their drug regimens, cause nausea, fatigue, whatever? Are there issues there that maybe you need to tweak something? And then the next thing is, if you predefine what is going to be quote unquote, if efficacy is what your goal, if are my treatment conditions credible? Well, you set ahead of time, as long as, you know, 8 out of 12 people have a positive response, we're going to say this is a credible treatment to move forward with. If it's fewer than that, then we're going to drop it from the future study, that kind of thing. So you're just trying to get at, is it even worthwhile? Okay. Now we're going to talk about study design. So this is literally, how are my subjects arranged relative to the factor level combinations or the treatments that I'm actually interested in? And this again can be specified by the researcher. It's usually driven by money, lab space, time, protocol, etc. So there's a lot of different examples. There can be a completely randomized where I literally just randomize my treatments to the subjects, whether they be animal, tissue, doesn't matter, human, doesn't matter, just completely randomize it. I can do what's called blocked. So if I have a bunch of different clinics participating, I can block on clinic. The idea of blocked is that every block or every clinic is a mini experiment in and of itself. The idea there being that any differences between clinics can be captured in this idea of just blocking on that. If every treatment is seen at every single clinic, I can capture what the variability due to clinic is without affecting the results of my treatment or inferences on my treatment. There are pre-post designs. So if I'm looking at somebody that has a torn ACL and I want to know, have they rehabbed their ACL to a good degree or back to where they were before, then is that really pre-post? No, but it's injury compared to a healthy limb. So that's the same idea. They're paired. The other piece would be, and we just did this, like a palliative care education piece, when you're working with people that have to deal with families that a loved one is dying and has gone into palliative care. There's ways you want to broach subjects of death and everything else. And prior to training, people have an attitude about how they feel about talking to people about death. And then post, you want to know, has their attitude changed? So we can kind of measure that. We can do a repeated measures design. So I'm going to follow these people at baseline, 6 months, 12 months, 18 months, and I'm measuring the same thing over and over again on every single subject. Then we have what's known as a nested design. So if you think, the easiest one to think of is trees, right? I'm looking at tree growth. Well, if I'm looking at tree growth and the leaf is what I'm actually sampling, I'm actually pulling the leaves off to look at how healthy they are. Leaves are nested within a branch, which is nested within a tree. So they're all built together, but the actual unit that I'm testing is that tree. I'm just using leaves from that tree to say how healthy it is. And then there's also what's known as a split or a crossover design, and that's where every subject sees every treatment. So every subject sees placebo, every subject sees, so let's say it's a drug study, I have placebo, I have the low dose of the drug and the high dose of the drug. Every subject sees each one of those levels. So the subject acts as their own control. All right. I'm not going to go too nuts in observational designs. This is more for your epidemiology class. I just wanted to let you know that they do have specific types of studies and they mean something. And this is actually taken from the North Carolina School of Social Work. So you have the cross-sectional study, so it's basically just, snapshot in time, single time point, much easier to do and manage. There's case control, so I find a bunch of exposures and then I link them to a control subject. So I have people that are, the sick and the ones that aren't, and I kind of link them together, match them on different things and follow them. Cohort, where I follow chunks of subjects through time. And then there's the ecological, where you're looking at the population level exposures and things like that and what's going on with regard to that. So it's more, let's see, what would that be? More the incident rates of a disease or something like that. Okay, so power analysis, we'll have a separate subject on this, or a separate lecture on this one. This is really just talking about the statistical procedure for determining the required number of subjects to detect a given difference. You'll hear people talk about it as a power analysis or sample size analysis. It's always the same thing. Should be driven by the purpose of the study. So if I'm doing a pilot or a feasibility, there isn't necessarily a power analysis that you're doing, because that's not the intent of those types of studies. Sampling design, next week we'll get a little more into this one, but basically what we're doing here is, how do I select the subjects that I want in the study, or that will be in the study, excuse me, not that I want in the study, that would bias it. So you've heard of stuff like this: inclusion, exclusion criteria, what allows you to be in, what doesn't allow you to be in, what is my target population, and how generalizable do I want my study to be. So that goes back to the context, right? How generalizable do I want this to be? The sample size analysis, again, goes into the sampling design, because the sampling design will inform what power analysis or sample size analysis I'm going to do. And then if you're doing an unpowered study, you can select a reasonable number to establish a decent standard deviation estimate, or you can power off a confidence interval, which we will all get to during this semester. So methods of sampling design, again, we'll talk about this in more detail next week, but there's convenience or cohorts. You basically just take whoever volunteers. You can do a simple random sample. So every subject that was in that ultimately ends up being in your group was randomly selected from the population, and they all have an equal chance of being selected. You can do a stratified sample. This is really saying, I want to balance on gender, I want to balance on race, I want to balance on what year you are in college, I want to balance on disease severity or injury severity, something like that. So I want to control, so I want to take appropriate proportions of people, so my sample is reflective of the group that I'm interested in, or the strata that I've identified. And then there's clustered. This is something you do if you're dealing with areas of very sparse population for whatever reason. So if I'm looking at like a Barrett's esophagus or something like that, there's a ton of normal tissue surrounded by some not so normal tissue, and I don't want to just randomly sample points in there, because I'm going to get a bunch of normals when my goal is to actually sample the Barrett's. So I'm going to look at where the tissue is cluster and shows Barrett's esophagus, and I want to sample randomly within those clusters that I've identified. Or if you're thinking of people and I'm doing a multi-state trial, I want to look at, maybe counties or zip code or something like that as my clusters, and then randomly sample from within those. And then systematic, this is one that you see a lot of times when you go through like security in an airport. They're taking every X, so every 9th subject starting at noon, the 9th person, the 18th person, and the 27th, etc., is going to be pulled off to go through a more intense screening process. All right, data collection tool, again, we'll talk more about this in next week. But this one does not need to be fancy. You just want to keep a few things in mind. You want something that's going to be easy for you to use, but you also want it to be easy to analyze after the fact. And we'll get into more detail again next week. But one thing you can do is each row represents a single subject, and columns represent the factors, comorbidities, demographics, whatever. But they're just, everything is its own column as far as what you want to collect. You want to collect to the finest degree of granularity that you can find, because I can always roll things up into bins later if I want to, but I can't unroll a bin if I didn't collect the original value. You want to avoid character strings, because most software programs can't handle it unless your goal is a qualitative study, in which case all you're doing is character strings. And then if you're in the planning stages at any point and you think you may be interested in something, you'll want to collect it. Now, if we're talking about people, you have to go back, and it's an IRB subject study, then you need to go back to the IRB and tell them, hey, I need to add this to my data collection tool, because that's one thing they are going to ask you. Okay, so the research design recap, or developing your research question recap, is context is very, very, very important. Just think about this for a second. If I have no context at all all I literally have is data. There's no information there. Information actually is data that has a meaning, right? Otherwise, I just have data points, and it really doesn't get me anything. So context is very important, and that's probably that whole context piece, the research question, all that is the hardest piece to really get at. Then the treatment design, what is important to you, right? One thing you don't need to do, but what is beneficial is if you make sure there's a professional community thinks it's relevant as well, because that makes it easier to get people on board with your study to begin with. And then the experimental/study design, really what you're after is what's most efficient for what you need to do and for what you want to answer. So what is your purpose, right? You want a design that supports all of those things. And there's the sample size analysis is going to be part of that. Then the sampling design, how am I going to acquire the subjects? Again, we'll get into more detail on that next week. And what data collection tool am I going to use? And here you just want the most efficient, meaningful way to organize the data for your analysis later on. So you don't want to be stuck with a bunch of handwritten pieces of paper at the end and expect somebody else to enter that stuff in. You'd like it to be upfront collected as you collect it and put where you want it to be put as it's being collected. And once you have all that, you conduct the study. All right. Hopefully this all makes sense. If it doesn't, please feel free to contact your instructor.